So today we'll be seeing the tutorial for the first week topic, which is on the state space solution and the realization. So the idea, first of all, the idea behind this tutorial is that we had discussed many theoretical results in the week 1. So with the help of this tutorial, we will see the direct application of those results onto some numerical examples. So if it requires some solving some equations or solving some matrices, we'll go through them. So this would be the outline for this tutorial, where the basic idea is to cover all those subtopics which we had covered broadly into this week. So we'll discuss the state space representation of LTI systems. Basically, given any system, how you can obtain the state space representation. Then we will see the time domain solution of those systems. So we will discuss both for the LTI systems, which in the first and second point, and the fifth and sixth and this last point. Then we'll see the realization, how to realize the LTI system and its equivalence between the given two LTI systems. So for your ease, we have also included that what are the slides number associated with the problems with which we will going to discuss. So the first problem is, consider this circuit shown below, where an electrical circuit is given to you containing some passive parameters, inductor, capacitor and the resistor, and there are two sources of inputs, the voltage sources E1 and E2. We need to find the state space representation for this given circuit. So using the Kirchhoff's law, we can analyze two independent loops. The first loop is this one, in which the current I1 is flowing, and in the second loop where the current I2 is flowing. So at the outset, we have specified two states. First is the current flowing into the inductor, which is IL, and another state is the voltage across the capacitor. The inputs are already pre-specified, which are given by E1 and E2. Now if we take this first loop, and if we see that in this branch I1 current is flowing, which is nothing but equal to IL, and in this and we suppose that in this branch I2 current is flowing, then in this branch we would have I1 minus I2. Okay, by using the simple current law. So first we'll write this first equation for this loop 1, which is nothing but E1 is equal to L di1 by dt plus R I1 minus I2, if we take the entire loop. Similarly, for the second loop, we can write minus of E2 because the current is flowing in the opposite direction, which is equal to R times I2 minus I1 plus the voltage across the capacitor. So after this simplification, we obtain this next equation, which you can see more closely. Now since we have chosen two different states, one is IL and VC, we want to represent these two basic equations in the form of the derivative of the IL and the derivative of the VC, so that we can form our state vector, which is basically x dot. So on the left hand side, we want the first derivative of the state vector, and on the right hand side we want to express them as a function of the state x and u, where u is your E1 and E2. Okay, and this function f, we know that it should be a linear map. So proceeding forward, using these two equations, it's just a simplification that we can write this I1 is equal to I2 plus VC by R plus E2 by R. Then substituting this third equation into the first equation, we obtain this one. All these steps we are doing so that we could have the first derivative of the state variable onto the left hand side. So after some simplification, we get this first derivative of the first state, which is I1 or is equal to IL, and on the right hand side we have the function of the input, which are E1, E2, and another state VC. Okay. Now going forward to some more simplification, we obtain this equation 5, which is VC dot is equal to again the function of the input variable, the state, both these states, and I1 is nothing but equal to IL. So after combining this equation which we have obtained in the last slide and combining this equation, we can write the state equation, the linear state equation in this form, where A and B matrices are obtained, these two matrices. So Y here are selected as the, so in fact Y could be the state also, because if you recall the output equation is given by Cx plus du. Okay, so depending on what measurements are available to us directly, we can choose the C matrix. If we choose C matrix as an identity matrix and D matrix is 0, in that case we would have Y is equal to X. Okay, so here we have chosen two different outputs. First is one of the states IL and another is current flowing through the capacitor. So if we choose these two outputs, then the C and D equations or C and D matrices can be obtained like this. It's just the simplification of those two basic equations which we have discussed in the first part of the problem. Okay. So after obtaining the state space representation of the problem 1, now our interest in computing the time domain solution of the LTI system. So for the computing the overall solution of the LTI system, we had studied that the overall solution can be represented as a summation of the zero state response and the zero input response. So here we'll compute three different parts individually. First we will compute the zero state response, where the initial conditions are taken as 0 and we want to see the output which is only influenced by the some certain input. The zero input response of the system, in which the initial conditions are in fact where the output the input in fact is 0. The overall response would be the summation of the first two responses. We have taken these numerical values to compute the numerical solution, and the initial conditions are taken as 1 and 2. We are supplying a specific input to this system, where the input is given by 1 and 2 by multiplied by a standard unit step signal, which meaning to say that this input, in fact on the left hand side we should have ut also. So meaning to say that this input is applicable starting from t greater than equal to 0 only. So before that the input is 0. Okay. So again, writing the state space equation into a similar form, where we have this x dot, this A matrix Ex plus Bu, and putting these numerical values what we have specified in the problem itself, then we obtained A, B, C, D matrices as these, and the initial conditions we are also provided to us. So if you recall from the lecture slide number 37, the zero input response can be computed by computing the state transition matrix. Now for the LTI systems, we had specified that the state transition matrix is nothing but an exponential matrix defined by e to the power a into t minus t naught, where t naught is the initial time, but here t naught we have taken as 0. So the response which we would be concerned with only e to the power at. Then once we have obtained the state transition matrix, we can compute the zero input response, which is merely the multiplication of the state transition matrix by the initial condition and pre-multiplied by the output matrix. So this is the response of the homogeneous system. Xt is equal to e to the power at into x naught. So after putting this e to the power at and x naught, we can simplify to this one. Now, if you have any difficulties in computing the matrix, exponential matrix, so there are a couple of ways to compute this matrix. The first method is to compute using the Cayley-Hamilton theorem. The second way you can compute, since we are dealing with the LTI systems, so you can use the Laplace transforms to compute this e to the power at. So first we'll compute the Laplace transform of this time domain function, and then again to obtain the time domain solution we take the Laplace inverse. Okay, then putting the C matrix, the exponential matrix, and the initial condition, we obtain finally this solution. So this is the zero input response for the given initial conditions. Computing the zero state response, you can refer to the slides number 39 to 41, where we have considered a non-homogeneous LTI system. Here we have shown explicitly that how you can compute this exponential matrix by using the Laplace transforms. So if you recall that the zero state response is basically given by this equation, where you need to compute the integral of this exponential matrix, which is a bit complicated procedure. So as an alternative, again you can simplify it by using the Laplace transform. So first compute the Laplace transforms and then compute the Laplace inverse to finally obtain the solution into the time domain. So this input is already specified to us, 1 and 2 with the unit step signal. C matrix is given to us, A, B, it is the Laplace transform of this input, the D matrix, and finally the U matrix. So after putting all these matrices into this equation, so a detailed solution is been given here. So you can verify by yourself whether all those matrices are rightly placed. So we won't go through the detailed of all the solution, just the simplification by putting all those matrices into the last equation. Okay. And finally, we would end up to this simplified version of the Laplace inverse of the S domain matrices. So once we compute the Laplace inverse, this is the solution we would obtain, which is valid only for t greater than or equal to 0. Okay. Now, as mentioned earlier, the overall response is given by the summation of the two independent responses we have computed in the first and second part. So after summing those, the zero input response and the zero state response, this would be the overall response of the circuit given the initial conditions and also with respect to the specific input. Okay. Now similarly, if some other initial conditions and some other input is given to you, so here we have taken the step type input only, where the first input was having a magnitude of 1 and the second input was having a magnitude of 2. Now instead of those step inputs, there are number of inputs by which you can compute the responses. So either you could use the ramp inputs, the sinusoidal inputs, or the impulse inputs as well. Okay, so with respect to each and every input, the response would behave differently, but with respect to initial conditions, you can parameterize and it would appear more or less the same, except the change in the numerical values. So the problem 3 deals with the state space realization of the transfer matrix. So here we have specified some transfer function matrix, which is a 2 by 2 systems, meaning to say we have 2 inputs and 2 outputs. And the realization problem deals with that given a transfer function, we need to see whether there exist this ABCD matrices. So if you recall the theoretical results, we have basically supplied the conditions that under what conditions we can say a transfer function or a transfer function matrix is realizable. And particularly for the LTI system, we have used some specific representation which we have also called the canonical representation, and that canonical representation was nothing but the canonical controllable representation. So we'll see that how you can obtain that specific representation, but at the same time we should not forget that the transfer function is a unique representation, but the state space representation is not unique. So we will obtain one specific representation. Otherwise there exist an infinite number of representations. Okay. So the results which we have discussed onto the slide number 67 and 68 of the lecture slides, we would going to use those results. So the first equation says that we need to decompose the complete transfer function into two parts. First part, which is or let's say the second part, which is the strictly proper part, meaning to say the order of the numerator is less than or strict or definitely less than the order of the or the degree of the denominator polynomial, and g hat infinity is when we have computed the value of the transfer function when s approaches to infinity. So the strictly proper part was given by this multiplication of this matrix, which is composed of the numerator of the numerator polynomial of the matrix multiplied by 1 by d of s, where d is the some polynomial of rth order given by this one. Okay, and once we have this matrix n of s, we have represented again as a summation of some constant matrices multiplied by the power of s. Okay, so we'll see in detail that how we can obtain these matrices. So g hat of s is given to us this one. So the first part, that what happens at when s tends to infinity, we can compute, and given by 0 0 0 minus 1. Now the strictly proper part is pretty much straightforward here. The matrix is already given into that form, where this part is directly you can take it as the denominator polynomial. The numerator polynomial we would take as this one, because if you see this first, second and third element, all those elements are having the degree less than the degree of this denominator polynomial, while this polynomial is having the degree equal to this polynomial. But we saw that the degree of this polynomial should be less than this polynomial. That's why we have extracted out this g hat infinity part. So after extracting this or decomposing this g hat infinity part, we can write this one as this one, because once you sum them up, you would finally obtain this equation. Okay. So this is, you can see as n of s, and this part which is in the denominator is d of s. Now this is a function of s. Now this, the maximum power here is s to the power 1. So first of all we will represent this constant matrix which is n1, and this one is n2, n1 into s plus n2. Again we have decomposed this complete polynomial into the summation of two polynomials with respect to the power of s. Okay, so basically it is to say that once you simplify this equation, simplify this terms inside the brackets, you would finally obtain this n of s. Okay. Now after obtaining all those matrices and the polynomials and the coefficients as well, this is the ad hoc representation or the canonical representation we have specified, where these alpha 1 to alpha r are the coefficients of the denominator polynomial. These matrices we have obtained already, g hat infinity, and this is nothing but only the identity matrix. So this p here is basically p is equal to 2. So here we would have IP would be an identity matrix of dimension 2. So this part is your IP and the rest is 0. Similarly, here we are having the scalar multiplied by the identity matrix of the same dimension. So here this is part is minus alpha 1p, and this part we have this minus alpha 2p. This one is this IP matrix, because p being equal to 2, we will have only this part. Okay, and this is just a representation of this one, and this one is a block matrix, a 0 block matrix of dimension 2. Okay, so this is the A and B matrices of the uh, given transfer function matrix. So again, you should not forget at the same time that this is only one specific representation. Now there could be another representations from where you can compute the same transfer function. Okay, and the output matrix being the P is equal to 2. So this one is N1 matrix and this one is your N2 matrix. And this one is D, which is nothing but equal to your G head infinity part. Okay, which is the basically the feed forward term into the state space equation. So above equations 1 and 2 are called the realization of the transfer functions. So this solves this problem number 3. Now the problem number 4 deals with the equivalence of the LTI systems. By equivalence we mean to say that given a pair of AB matrices, we want to see that whether these two pairs denotes the same system, right? So first pair is this one with the numerical values, and another pair is with A bar B bar with different set of numerical values. So we want to verify whether these two pairs actually represent the same system or not. Okay. So here we have listed two methods to find out whether these two pairs are equivalent or not. So in the theoretical results, you would recall the key ingredient is to find the transformation matrix T or P, so that these AB pairs are related by that transformation. So those transformation matrix could be obtained in a number of ways. Say for example, if I take this B matrix, starting with this B matrix, and I uh, do this operations, that the row 2 is replaced by the scaled value of this row. So I would obtain this one B matrix, and this B matrix, if you see that it is nothing but your B bar matrix. By doing simply this row transformation or this operation onto the second row of the B matrix, we obtain this B bar. So in that case, this transformation matrix is simply given by this one. Okay, you can also verify whether the transformation relation between the A and A bar matrices are also satisfied for this transformation matrix. So this is done in this slide here, where we are taken the same T matrix multiplied by A, T inverse should be equal to A bar. So after simplifying all these inverses and the multiplication, we could actually verify that this transformation is verified. So with this T matrix or this transformation matrix, we saw that these two pairs basically represent the same system, or they both are equivalent. Now here we have an advantage, because if you recall this equation, B bar is basically given by T into B. If there exists any T matrix by which B bar and B are related, at the same time, if A bar and A are related using this equation, we say that T is transformation matrix. Now Here we have an advantage that B is a square matrix, and on the top of that, B is in fact non-singular. So if I pre-multiply by B inverse into this equation, I can obtain the T matrix directly. Say what I mean to say, that this equation is given to us. If I pre-multiply by B inverse, I would have B bar B inverse is equal to T. So I can obtain directly the transformation matrix by the multiplication of the B bar and the inverse of the B matrix. And this is what we have done here. So this T is extra. So it should be B bar B inverse is equal to T. And after simplifying, we obtain this T matrix. Okay, now for the singularity, you can verify that the determinant of this T matrix is not equal to 0, meaning to say that it is non-singular. So this was in fact the condition, that if there exist non-singular T matrices by which these two relations, first between the A bar and A, second between the B bar and B, are related, then those two pairs are equivalent. So we have computed in fact two different non-singular transformation matrices by which those two pairs are equivalent. Now you can verify by yourself that for this T matrix, the first relation, that is A bar is equal to T A T inverse, should also be verified. Okay. The problem 5 deals with the state space representation of the LTV system. So here for the LTV system, we have assumed that all those parameters, passive parameters, which were having some constant value in the first part of the problem 1, we are assuming that all those parameters are now time dependent parameters. Okay, the inputs would remain as it is. So now if you apply the superposition principle on this circuit, you would see that it satisfies the linearity, but it is time variant because of the parameters being time dependent. So the idea would remain the same, that we have the two loops, and just one point to note here, that once we write the equation of the first loop, since L was a constant parameter in the problem 1, we have directly represented the voltage across the inductor as L diy1 by dt. Okay, but now here we have L as a time dependent parameter, so we should have the derivative of uh, the flux around this inductor, which is Li1. Okay, so this part we have used here. So be careful while writing the loop equations when we have the time dependent parameters in contrast to the time independent parameters. So writing the loop equation for these two different loops and doing the simplifications, and so we won't discuss through all these simplifications. You can see more closely whether you are also able to obtain these simplification. The idea is that on the left hand side we need the first derivative of the two states, and here the states variables remains the same to the problem 1, and on the right hand side we need some function which is a function of the state and the input, right? So from equation 2 we get this. So another point, that here also once you start writing the equation for this capacitor, for this loop equation, so here Q is basically given by the CV, and we are taking the current and the voltages. So you need to take care when you take the derivative or the integral, because here now C is not a time independent, right? So this is taken care here once we write the voltage equation for that loop. that the current we are taking is the derivative of the charge stored on the capacitor. Okay, and charge is C into V. So after simplifying these two equations, this is the state space representation we have obtained, where this is the state variable, this is the A of t, the time dependent A matrix, and similarly we would have time dependent B matrix. Okay, and this is U, this is X, and this is X dot. Okay, now for this problem 6 also deals with the state space representation of the similar circuit, but here we have chosen different state variables. So in the problem 5, the state variables were chosen as the current flowing through the inductor and the voltage developed across the capacitor. Now here we have chosen another state variable, and we want to see whether with respect to those state variables we can again obtain a similar kind of state space representation. Right? Now we also know at the outset, if the states are different, and since the system is known to us already, so we would going to have some representation, but in that case the A and B matrices would entirely be different. So here we have chosen these states: the flux through the inductor and the charge across the capacitor. The inputs are already pre-specified as E1 and E2. So these relations we basically know from our +2 physics. So again, writing the loop equation for both the loops, you can go through in more detailed simplification of those two loops in terms of the phi and the charge. So doing further simplification, we obtained this equation where again we have this A of t and B of t, and this let's say I would say another state variable x bar, and here we have this x bar and the u remain the same. So if you match those AB matrices with the solution of the problem 5, you would notice that these two matrices, so it is better to represent these matrices by bars as well. Okay, so that we are not confused that whether the A and B matrices remain the same. Okay. Now, if we want to see the equivalence between these two different representation, so this problem is in fact trivial. Why? Because generally we are given with the AB pair at the outset, and from that given AB pair we want to see that whether there exists an equivalence without knowing the system. But here the system is already known to us, and for that system we have two different state space representation. Now if we want to see the equivalence between those two state space representation, that would definitely be there, because those two representation belongs to the same system. So we just want to verify that the application of the result we had seen for the LTV case. Okay, so these are the two representations, one in terms of the state variables. Let's denote this state variable as x, x, IL and VC, and another we have x bar, which is phi and q. Okay, so if you recall the lecture slide number 56, this is the condition we have given that the two pairs, time dependent pairs, are equivalent whenever there exists a non-singular matrix P of t. So here we have specified already a dimension, because the dimension of the state matrix is 2 cross 2. So we are looking for that matrix P, which is a square matrix of dimension 2, such that these two relationships are satisfies between these two pairs. Okay, so we need to find a P matrix. If there exists a P matrix, these two matrices are equivalent. Okay, so there are two methods once again. So one is by doing the uh, row operations or the column operations, by which we want to see the equivalence between first the B and B matrices, and after obtaining the transformation matrix through those operations, we want to verify that the first relationship is also verified. Because at the same time we should know that P of T should be a continuous matrix. Okay, so this is the first method by doing the elementary row operations, and this is the final P of T matrix we have obtained. Okay, now to verify that P of T is the algebraic equivalent transformation matrix, substituting in 1 we obtain this A bar as this one. Okay, P of T, A of T, this is the derivative of P and multiplied by the P inverse. So after doing the simplification, we finally obtain this A bar, meaning to say that that P matrix is basically a transformation matrix for the time varying system. Going to the time domain solution for that LTV system. So here we are taking the AB matrices as this one. So if you see that these AB matrices are possibly the matrices which we have written for the second part, considering this phi and this charge as the state variables. Okay, so there are 2 points we want to solve here. First, we want to comment on to the realizability, and the second point is the we want to compute the fundamental matrix. Okay, so note that here, first of all, once you see this equation, that the computing the in fact the state transition matrix for an LTV system is pretty much difficult, and we have discussed one scenario that if the state matrix considering the 2 dimension, it is given as let's say into this form, into this upper triangular form, where the element inside this triangular are non-zero or could be non-zero, but this one should definitely be 0, right? Now if we have an A matrix into this form, uh, in fact we need to see, so we need excuse me, so we need the A matrix. In fact it should not be this one, so the A matrix should be some, they could be non-zero element, but this one should be 0 in fact. Okay, so this triangular, upper triangular, we should have. Why we do this? So that if we have the state variable x1 dot x2 dot equal to this one x x1 and x2, we should be able to write that x2 dot is some element x2. Okay, so it becomes automatically a decoupled system. At least the second state is decoupled and we can solve it separately, and once we have the solution for this x2, we can put it into the equation of the first, and then we can obtain the solution of x1. and then using the concept of the fundamental matrix we can finally compute the state transition matrix. But here if we see this A matrix, it is not into this form, because if I write the two equations we would have x1 dot is equal to minus 2 by t, x2 by first equation. This is only the homogeneous part I am writing. I am not considered or not concerned with the B matrix for the moment. And the x2 dot I would have 2 by t x1 minus 1 by t x2, right? So now I cannot solve any of the equations separately to compute the solution of the state metric state variable. So this is pretty much difficult. So to address this issue, first of all we'll try to see whether given this A matrix are we able to obtain either this matrix into this form where the x2 state can be computed separately, or either the x1 state can be computed separately. In that case, if we want to say that the x1 state can be computed separately, we should have another upper triangular form which should be some non-zero, and this should be 0, and this could be non-zero element. Okay, so that if I write the equation of the first equation, I would have x1 dot is equal to some non-zero function of time into x1. Okay, so first we'll convert that A matrix into the form so that we can compute the fundamental solution. So by doing this row operation onto this A matrix, we obtain this A bar matrix where it is into that perfect form by using which we can compute the fundamental matrix and finally the state transition matrix. So since we have performed the row operation, and this state matrix A bar could be in terms of another state variable, so we have represented that state variable by z, and these z state variable could be any variables or could have any physical meaning onto that electrical circuit. So solving this equation, we can separately solve this z1, and then putting the solution of this z1 into this second equation, we can solve separately this z2. Okay, the solution for z1 is given by this one, and the solution for z2 is given by this one. Now these two solutions are specific to these initial condition. Now if you recall the computation of the fundamental matrix, we specify we need at least two vectors which are linearly independent, so that once you compute the fundamental matrix, that fundamental matrix is non-singular. So first initial condition we have specified this one, and another initial condition we need such that both these vectors are linearly independent. So another natural choice of the initial condition would be 0 1. So we choose this 0 1 as another set of initial conditions, and with respect to these initial conditions we solve for z1 and we solve for z2. Now with respect to those initial condition and whatever the solution we have obtained, we compute that fundamental matrix, we call it zt by capital ZT, which is the fundamental matrix with respect to the new state variables z1 and z2. So this is the capital Z of t. Now since these two fundamental matrix, so this is also one of the result we had studied, that if the two pairs are algebraically equivalent, their fundamental matrix would also be equivalent or would also be related by using this transformation matrix. Okay, and this transformation matrix we have obtained by from the elementary row operations we have performed initially. So using this T inverse and capital Z, we obtain the fundamental matrix for the original state variables. Now using this this matrix, we can compute the state transition matrix and finally the solution of the or the time domain solution. Now talking about the realization, so this was one of the important result which was given on the slide number 74, that if the impulse response of the system is given to us as gt comma tau, we say that this impulse response is realizable if and only if that impulse response can be decomposed into this form, where this M and N matrices were parameterized in terms of the fundamental matrix. So for this system, if I write the impulse response, I can write this one, where the C matrix, you can assume it as an identity matrix. The D matrix can be assumed as the zero matrix. So the rest part remains the same. So if we compare these two terms, we see that your MT is nothing but equal to X of T, the fundamental matrix itself, and N of tau is basically your X inverse tau and B to tau. Meaning to say, so we are able to find such two matrices M and N, such that if any impulse response is given to us, that we can say that this impulse response is realizable. Okay, so by realizability we actually mean the physical implementation of that impulse response. Now this impulse response, since we have computed from a practical electrical circuit, so it was trivial that that impulse response would be implementable. But since we want to show the application of those theoretical results, so just for the sake of that, we have shown that how these M and N matrices can be computed. Okay.